Okay, number one, you're given a polynomial and you're asked to find what degree it is. They determined it was a degree 4 polynomial, which would mean what? The fourth difference was constant. So notice that all the x's are over equal intervals. Up 2, up 2, up 2, up 2, up 2. That's the reason you can do this, because they're equal intervals in the domain. Any questions about what they did or finding it was a degree 4? Everybody's good with that? Okay. 2, the graph of a quartic, which again is degree 4, polynomial y equals f of x is shown. Determine how many x-intercepts there are. So all we're looking for x-intercepts, how many times does it cross or touch the x-axis? So right here is an x-intercept, there's an x-intercept, and here is an x-intercept for 3 x-intercepts. How many relative minima are there? So just the minima, relative minimas. There'd be a relative minimum here at the valley and there at the valley are your 2 relative minimums. Minima. Sorry. No such thing as minimums. Okay, how about relative maxima? Well, there's only one, so it is a relative maximum here at the peak. Questions about relative maximum, relative minimum? D, how many times does the graph of f change concavity? So I would just look from left to right. As we first happen upon the graph, this is concave up, right? Because it is a U shape. And then at some point here, it switches to an umbrella shape. So the point that it switches is an inflection point. That's a change in concavity. So then is it an umbrella the rest of the time? No, at some point it switches back to being a bowl, right, or U. And that point is here. That's a second inflection point where it changes concavity. So it's concave up, down, and up, which means it changes concavity twice. Questions there? So there's 3 different concavities, right? There's a concave up section, concave down, concave up, but there's only 2 times it changes because it has to start out as something. So it starts out as concave up. Label the absolute minimum and explain why this value, or explain why this value does not exist. That's what we say. How can you label it and say it doesn't? So relative or absolute minimum would be the lowest y value the graph ever takes on. That appears to be here, is the lowest possible y value. So this is an absolute minimum. Not only is it a relative minimum, it's an absolute minimum. And so they've labeled that A. Questions there? Label the absolute maximum B, or explain why this value does not exist. So for what we can see, the absolute maximum is here, right? This is the highest y value. But we assume this graph continues up forever because there is no endpoint. So absolute maximum, you're trying to put a roof on the top, cap it. You can't cap it. It goes up forever. So there would not be a relative, or there would not be an absolute maximum, sorry, because f is increasing forever. So there's no highest value. Questions there? 3, a polynomial function g has x-intercepts at 0 and 4. Which of the following statements must be true? So A says g must be a quadratic function. That's not necessarily true. So we haven't talked about this yet, but a degree 2 polynomial, which would be a quadratic, it can have at most two x-intercepts. It can't have more than two x-intercepts. But we have seen quadratics that have one x-intercept and zero x-intercepts. So just because it's a quadratic does not guarantee it has two. So similarly, degree 3 polynomials can have at most 3 x-intercepts. They can have 2, they can have 1. A degree 3 can't have 0. If you think about it, why could a degree 3 not have 0 x-intercepts? We're going to talk more about that today when we talk about turning points and roots, and tomorrow when we talk about end behavior. Yeah, a degree 3 polynomial is a snake, right? It's a Gary. So if it goes in different directions in the y-axis, it has to go through the x-axis at least once. Okay, now it can, 1, 2, 3. This could be a cubic function, this degree 3, that has 3 x-intercepts. And how could I draw one that has 2 x-intercepts? I could go here. Now it's a degree 3 polynomial with 1, 2 x-intercepts. So just because it has 2 x-intercepts, we don't know it's quadratic. Everybody understands why? Degree 4 can have at most 4, but they could also have 2 x-intercepts. Degree 5 has at most 5, and so on. B, G must change concavity on the interval from 0 to 4. So the way that I would try to solve this is I would try to come up with a counter example. If I can think of one graph that I can draw that has x-intercepts at 0 and 4 and doesn't change concavity from 0 to 4. Does that change concavity at any point? It's concave down forever. So is it guaranteed, just because we know it has 2 x-intercepts at 0 and 4, is it guaranteed to never, or that is it guaranteed it must change concavity? No, there are some examples where it doesn't change concavity. C, G has an absolute maximum or minimum at x equals 2. Okay, so if we knew it was a degree 2 polynomial, which is a quadratic, it would have an absolute maximum or minimum at x equals 2 because there's an axis of symmetry. But it goes back to we don't know for sure it is degree 2. It could be like this, degree 3 polynomial that I drew with 2 x-intercepts. So let me just change this to make it fit my criteria. It says that we must have x-intercepts at 0 and 2. Okay? Is it guaranteed that the absolute max or min is at 2? So 2 would be halfway here. That would be this point. There's no guarantee that it happens exactly halfway between them. There is a relative maximum or minimum somewhere between there, but it doesn't have to be at 2. It could be shifted. Okay? And the last one. G, there's a relative maximum or minimum on the interval. Well, if you think about every example I've drawn right here, this has a relative maximum. This one has a relative maximum, and it also has a relative minimum on 0 to 4. So can you draw something that crosses or touches at 0 and 4, but doesn't ever have a max or min between them? I mean, if you think about it, if I bounce off at 0, I got two options. I could bounce or cross at 0. If I bounce at 0, how could I get back to the other x-intercept? I'll have to turn back to have a relative minimum. Or, okay, what if I cross at 0? Okay, well, if I cross at 0, what has to happen? It still has to turn back at some point to get to 2, no matter. So there has to be a max or min. The only way there wouldn't be a max or min is if at 0 and 4 it was horizontal. Sorry, I couldn't think of the word. Why can this not happen though?
Because there would be multiple x-intercepts.
There would be more than just x-intercepts at 0 and 4. Right? There would be an infinite number of x-intercepts between 0 and 4. So this can't happen. So it has to go up or down. So there has to reach a max or min at some point to turn back. Today we're going to look at another key feature of polynomials. They're zeros. So what's another word for zeros? Roots, x-intercepts, solutions, right? All mean the same thing. So we're looking at their x-intercepts. It says use Desmos to graph the polynomials. We're not going to use Desmos. We're going to use our graphing calculator. Okay? So first it tells me to graph g of x equals x minus 2 times x minus 2 times x plus 3. So think back to what we were looking at with a quadratic function. Degree 2 polynomial. What form is this in? Factored form. This is still factored form of a degree 3 polynomial. So what does a degree 3, what does factored form do a good job of showing us?
The x-intercepts.
The x-intercepts. Guess what? That still happens here. So as you're graphing this, as you're typing it in, I want you to think about where you think the x-intercept should be. And if you need help typing this in, or if your graph doesn't look great, just let me know. X is right beside alpha. It says x, comma t, comma theta, comma n. It's okay. I'm getting good at saying that. I don't even have to look at it anymore. Here's what my graph looks like. If your graph isn't centered, you can let me know. I can show you how to center it. If you would like the grid like I have on my calculator, I can show you how to do that. Whatever you guys would like. Okay, so what I want you to click zoom, and you click 6 for zoom standard. Let's see if that fixes it. And if not, then we're going to look at what you... There we go.
Okay.
There we go. So that's, I would still go zoom 6. That's the easiest fix if it'll work. And you'll go to zoom standard. And yours should look like mine. Mine's in zoom standard. Anybody else? I know we haven't got to go over the graphing calculators much yet. But I think now might be the time.
Mine gives a syntax error.
That probably means you... Let me see your y equals. It's because of this one. You have a secondary one here that is trying to graph.
Okay.
That wasn't finished.
Alright, thank you.
Anybody else? So when you were thinking about factored form for a quadratic and finding the x-intercepts, where do we think the x-intercepts are going to be just from looking here? This one will give an x-intercept at 2. So the x-intercept of 2 happened twice, and negative 3. So if I look here, my x-intercept should be at 2 and negative 3. Well, they are, but they're different kinds of x-intercepts. At negative 3, the graph crossed. At 2, it bounced. Does anybody know why? How do I know whether it's going to cross or bounce?
If you got the x-intercept twice, that means it technically didn't go through it.
That's correct. So because the x-intercept is occurring 2 times, we call that a multiplicity of 2. You guys seen that? Heard that before? Okay, no. So for a polynomial graph, when an x-intercept happens an even number of times, 2, 4, 6, 8, that means it's going to bounce off that x-intercept. So let me say that again. When an x-intercept has an even number of multiplicity. That means how many times the x-intercept occurs. Here, the x-intercept at 2 happens twice. So that's an even multiplicity. That means at that x-intercept, the graph is going to bounce, not cross. If it has an odd multiplicity, if the x-intercept only happens 1 time, 3 times, 5 times, 7 times, it's going to cross at that x-intercept. If the multiplicity is 1, it crosses like this, just a regular crossing. If the multiplicity is 3, 5, 7, 9, it snakes at that x-intercept. So again, let's just identify the x-intercepts were at 2 and -3. The y-intercept, could we see where the y-intercept was at on our graph? Not quite. So here's what I want us to do. To find that y-intercept, is everybody, am I going too fast? Too fast? Too fast? Click window. We need the y max to be higher because I can't see exactly where it crosses. So the y max would happen at, let's just say 15. And if I graph that, it's still not quite high enough. So if I go window, let's try 20 as the y max. Oh, I'm an idiot. I'm putting it in my x max. No wonder it's not working. Did 15 work?
20 works.
Yeah, 15 works too because I'm a moron. I was wondering, why is it getting farther off center? Yeah, it looks like it crosses at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Here's another way you can find that. Like if it's a really high number and it's hard to count. Is everybody ready? Is everybody ready? Everybody ready? Click second, trace, to pull up calculate, and let's click value. So I want to know what's the y value when x is 0. So you see how it says x equals blinking? I can go x equals 0, and it will spit out y equals 12 at me. So even without seeing it on the graph, you could do that anyways. I need to walk through that again for anyone? So the y-intercept is at 0, 12. What's the degree of this polynomial? It has 3 factors, so it's a degree 3 polynomial. How would you say the factors relate to the x-intercepts? So if I have a factor at x minus 2, what x-intercept did that give? 2. So the factors are the things that multiply together. So here I have a factor at x plus 3, which means the x-intercept is at -3. So how are the factors and x-intercepts related? They're opposite signed. X-ints are opposite sign of the factor. So I think they wrote that question wrong. I think it should say, what is different about the behavior of the graph at x equals 2 and x equals -3? So let's fix that to say -3. And I've kind of already stolen that question. Right? So they're really looking at the 2 x-intercepts. So what's different at the 2 x-intercepts? Absolutely. So at 2, the graph bounces. At 3, it crosses. And they use the terminology through instead of crosses. I'm gonna have a hard time changing that. It's the same thing. when we look at everything that's happening on this graph, we have an x-intercept here. It's concave down, right? Then we reach a relative max somewhere up here that you guys can see, and then it has a y-intercept. Then somewhere right in here it switches from concave down to concave up, and then it has a relative minimum here, and then it's concave up forever. So this was a degree 3 polynomial. Did you guys know how it's degree 3? Is everybody good with that? Because it has 3 factors. Another way you could think about it is if I distributed this out. Think about distributing it. What's the highest power of x, the highest term with an x degree I would have? It would be a degree 3. You could think about distributing just the x times the x times the x. And that will give me the x to the third. Similarly, if I want to find the y-intercept, where did the y-intercept happen in a quadratic? When we were in standard form, the y-intercept is the constant number that's at the end. So if I wanted to find the y-intercept without graphing, just distribute the constants. Negative 2 times negative 2 is 4 times 3, 12. That's going to be that last term. All the middle terms with the x to the second and x to the first, you would have to distribute to find those. But if you just want the degree, you can distribute just the first part. If you want the y-intercept, just distribute the last part. Okay, cool. Questions? Out a calculator. We'll do that in a second. We'll see if we can graph one without the calculator in a second. But let's go ahead and look at this one. Like before you graph it, do you guys know where the x-intercepts are going to be? At 2 and at negative 4. What's the multiplicity at 2? 3. So what's going to happen? It's going to go through and it's going to snake, like a Gary, through 2. Okay, and then what about at negative 4? It's going to go through again because it has a multiplicity of 1. So see, just kind of, like just by me looking at this, I already know some characteristics before I graph it. That way I know if my graph looks way off, I typed something in wrong. Right? I kind of have an idea in my head. Can I find the y-intercept without graphing it? Well, if you think about it, this parenthesis is happening 3 times. So negative 2 times negative 2 times negative 2 is negative 8. Negative 8 times 4 is negative 32. So the y-intercept should be at negative 32. What's the degree of the polynomial? 4. Okay, so see, I answered all their questions without even actually graphing it. But let's go ahead and put it in my calculator. It should be x minus 2 cubed times x plus 4 graph. So I can't see the y-intercept, so I'm going to change the window. I think the y-intercept should have happened at negative 32. So I'm going to put the y-min at negative 35. Right? I can see the y-intercept there. I can't see that local minimum, but I can see the y-intercept. We understand about changing the window, why I did what I did. So look, at negative 4, it crossed like I thought it would. Its y-intercept, this is 35, 34, 33, is 32, negative 32, like I thought it was. At 2, it snakes, like I thought it would. Right? I already knew some key characteristics without having to graph it because of the factored form of the polynomial. So if I think about it, what is my graph right here? When I first start, is it concave up or down? It starts concave up. Down here somewhere it's going to reach a local minimum, right? It's going to be the low value, local minimum. Then it starts back up, still concave up, crossing the y-axis here. Okay, does it ever switch to concave down? Yeah, it does, somewhere. I guess somewhere right in here, where it starts looking more like an umbrella, but then it switches back to concave up at the x-intercept. Questions there? I've touched on multiplicity. Everybody understands what that is? That's supposed to be one of my special notes that we make now. So let's see. Can you determine the roots? Those are x-intercepts when it's in factored form. Can you find the y-intercept? Can you find a turning point? Once it's graphed, you can. So all a turning point is a point of inflection where it changes from concave up to concave down. That's a turning point. Another word for that. And the factors. We know what the factors are. X minus 2 is a factor that happens 3 times. X plus 4 happens once. See, look at there. We've already, look at that, man. We just write that up there every day. What's the 1/2 doing? It's a vertical compression. So on the outside, it's less than 1, so it should be compressing the graph. What's this giving me? This is giving me a x-intercept at -3 with a multiplicity of 1, which means it crosses there. Crosses. Here at -1, I have an x-intercept with a multiplicity of 1, so it crosses. This is different. What's different here? There's a squared on the inside. So, just thinking about it, how are we finding the previous x-intercepts? Like, how did you know this was at -3?
Because we plug in -3 equals 0.
Yeah, so what we do is we take our factor and set it equal to 0. Because what am I really setting equal to 0? The y value. Well, x-intercepts have a y value 0. Do you guys remember me doing this whole spiel whenever that was, Thursday? So if I set this factor equal to 0 and solve, I know then when y is 0, the x value is -3. That gives an x-intercept. So if I do the same thing here, what would happen? If I took that factor and set it equal to 0, x squared would be equal to -4.
It does complex numbers.
What do you mean, how?
Can't square root of -1.
Not in the real numbers. You're correct.
You gotta do the imaginary.
You're correct. Can't take the square root of a negative in the reals. So, just think about this. Just think about this. This is a root, a factor. Is this an x-intercept you can put on a graph of the real numbers? No. So, it still is a root. It still makes it be a degree. What degree is this polynomial? 4. It's still a degree 4 polynomial. But remember how I said degree 4 polynomials can have at most how many x-intercepts? 4. Degree 4 can't have more than 4. Well, guess how many x-intercepts this is going to have? 2 reals and 2 imaginary. Just real quickly. Imaginary numbers are very valid numbers that give real solutions. That's a bad word. They give valid solutions that are used in engineering and sending spaceships up to... Okay, imaginary numbers are useful. They're named poorly. So imaginary doesn't mean useless, and it doesn't mean I can't use them. It just means... It means they're not real.
They're fake.
No, they're imaginary.
What does imaginary mean?
Look, I've never worked at NASA, I'm not an engineer. I've never had to use complex and imaginary numbers before, but they do use them. My Cal 2 teacher, have I told you about my Cal 2 teacher? Dr. Abercrombie, that taught my grandpa. He taught my grandpa math at Jacksonville. Have I told y'all? Yes, no. So he worked at NASA in the 60s, 50s. He talked about using complex numbers. There's even another branch of complex numbers that's called a quaternium. Just had to Google it. I just had to trust him because I have no idea what he's talking about. So they're really there. I've seen it when I've Googled it. I was like, yeah, he's not lying.
It's kind of like when you have no friends in your childhood, your imaginary friend is still useful.
Okay, yeah. So the x-intercepts are at -3, 0, and at -1, 0. So while these give me roots, they're not considered x-intercepts because it doesn't cross the x-axis there. What did we say the degree was? 4. How many solutions are there to the equation f of x equals 0? So what they're saying is when you graph it, how many x-intercepts did we see? We saw 2. So here's the way they answer that. There should be 4, but only see 2. I want this very basic. Why does this give an imaginary solution? That's what I'm looking for. You can't take the square root of a negative. That's why we get imaginary roots. And then it says, what are those imaginary roots? So if I've got x squared equals -4, you guys said you need your other calculator to do imaginary roots. Are you scared of doing this root? Really?
No, I'm just saying, like, when it's like a big one, I'm doing the other. I'm getting my other calculator.
Can y'all guys do this square root without a calculator?
We did it last year.
Do you know what the square root of 4 is? 2. So here's what you got to do. -4 is just -1 times 4. The square root of 4 is 2. The square root of -1 is. That is the definition of the imaginary unit. So I took the square root of -1, which was I. The square root of 4, which is 2. That's where I got 2i. But here's the caveat. How did I get this step? I chose to take a square root of both sides. Every time I make the choice to take a square root, I must account for 2 possibilities. Plus or minus. When you choose to take a square root, you must account for 2 possibilities. Plus or minus. That's different than if the paper already has the radical on it. If the radical is already on paper, all you have to worry about is the positive or the principal square root. But when you choose to take a square root, you must account for plus or minus. Anyways, that's another tangent for another time. Questions on 4? 5. Can a quadratic equation ever have one real and one imaginary solution? Explain why or why not. Oh, so this is a good thought. Good thought. What does it mean if it's a quadratic equation? It's a degree 2 polynomial. So what's the maximum number of roots it could have? 2. So can it have one real root and one imaginary root?
No. Because they would have to bounce off, and that would make it, for it to have one, you would have to bounce off of it.
So if it only had one root, so you're thinking about graphically, I like that. If it only had one root, it would have to bounce off of that root.
But then that would make it have 2.
But then it'd have to have 2 at that one root because it would have to be a perfect square. That's a cool way to think about it, graphically. I like that. That's not the way they think about it, but that's correct. Like nothing you said's wrong. Okay? I'm telling you, that's a good answer. I'm just telling you, as I give this other answer, don't think, oh gosh, I missed that. That's right. Okay? You guys understand what she's saying? Thinking graphically. If I knew it had one real root here, well then it has to turn up to be a quadratic. It would have to have a second real root. The only way it wouldn't have a second real root is if it bounced off at that root, but then that root would have a multiplicity of 2, but it only happened once. Yeah, that's cool. Okay. Another way you could think about it, that's right. Can I say it again? That's correct. Another way you can think about it, if I had an x-intercept at -2, and let's say the other x-intercept was at -3i, okay, what would this polynomial look like in standard form? X squared plus 3xi plus 2x plus 6i? Was this a quadratic form? And that's standard form. Do I have any like terms? No, I got nothing I can combine. Was that what a quadratic looks like? No, in standard form it should be of the form ax squared plus bx plus c. Complex roots always come in pairs. That's what we need to learn there. So there's your little note. Complex root come in pairs. Does anybody know what we call those pairs of factors? You may not have ever seen this word, but boy, we're going to see it all the time now. I'm going to start just writing a letter at a time. No, I like the guess. But like how she was still kind of right, that one wasn't. But I like the guess. I still like the guess.
Concave.
It's not concave.
Conjective.
You're close.
Conjunction.
You've obviously never seen this word.
Oh, I have seen.
Oh, I've seen a conjugate before.
That might be.
It's the orange one.
Is it
I don't think it's in that row.
at 10? At 10.
The orange one at 10. I think it's in the middle.
Thank you. Conjugates. That's so hard to find the right font. Why did I start at the back? I started at the front. That would have been so much easier. So what a conjugate is, if I have a factor that is x plus 2, its conjugate would be x minus 2. Those are real factored conjugates. Imaginary roots always come in conjugates. So if x plus 2i is a factor, x minus 2i is a factor. Every time. They always have conjugates. So you could think about how one of your special cases of factoring, it would factor to be the difference of perfect squares. And so what's great about distributing the difference of perfect squares? You get x times x, which is x squared. The middles cancel. Minus 2x plus 2x goes to 0. Minus 4. That happens with conjugates too. The middle two terms cancel. So x times x is x squared. 2i times negative 2i is negative 4i squared. I squared is the same thing as negative 1. So I can substitute in negative 1 for I squared, and the imaginary number goes away. And it's a real coefficient polynomial that can be a quadratic. Polynomials, the things we're working on, polynomials must have real number coefficients. They can't have imaginary coefficients, or they wouldn't be a polynomial by definition.